take you basically step by step from the very beginning till the state of the art concerning this particular computation of correlation functions, and you will then have this notebook and you can play with and go deeper or go broader. So I will try step by step to take you to the state of the art in this particular computation that I'm going to describe, and in the last lecture I will try to comment on the overview about what lies beyond this particular computation, how this connects to other works, where this fits exactly in the landscape of trying to solve n equals 4 superunions. Okay? So these lectures will be organized. I will start by introducing what's called the CFT data. What is the CFT data? The structure constants and the anomalous dimensions. Then I will go on to review a few things about the spectrum and spin chains. And I urge you to ask me to speed up, because many of these things I'm sure Benjamin and Collie already told you about. So please let me know and I will speed up at this point when needed. And then I will go to the computation of structure constants in n equals 4 superunions, and then we will come back to data and spin chains. So basically the path will be something like this along these 4 lectures. So we'll be going back and forward between the CFT data and the conformal bootstrap that I will tell you now, the spectrum, 3-point functions, back to the conformal bootstrap to analyze a little bit of data, and basically I will try to explain you what this notebook here does as we go along. Does everyone have internet and access to this website and to this notebook here? Yes? Okay, so please download it at some point and we will use it a little bit later. So let me start right away with reminding you why in a CFT are we so interested in these two sets of numbers, the anomalous dimensions and the structure constants of local operators. So consider a correlation function of 3 operators, O1, O2, O3 in a CFT. Let these guys be scalar operators of dimension delta, delta 1, delta 2, delta 3. And let me remind you of a couple of things that you know. Basically, this 3-point function, on the one hand, you know that it is totally fixed by symmetry up to a number called the structure constant, and it takes this form, x1 minus x2 So just conformal symmetry tells you that the structure constant of 3 scalar operators is totally fixed by symmetry up to 2 important numbers, the structure constant and the dimensions of the operators. So let me now go on and tell you a little bit about the implications of conformal symmetry for the study of higher point functions such as 4-point functions and so on. So for that, let's stay a little bit longer with the 3-point function and consider the operator product expansion of these 2 points. That is, we look far away at this, we take these 2 points to be close and this third point to be far away, and we replace these 2 points here by a sum over all operators. Let this be all primary operators, and then we have a structure constant, Ck. Let me see, okay. A structure constant, the OP between operator 1, 2 producing operator k, and then I have the 3-point function between operator OK and operator O3. And this guy is, say, at x2. Okay? So now let's fill in this equation. It's not correct as it stands. So this structure constant, we can sum over the primaries, or we can sum over descendants. So this OK can be a primary, or it can be a derivative of a primary. So we can have also any number of derivatives, d mu1 up to d mu n, that act on x2. So these are derivatives with respect to x2. And therefore, these CSM indices, mu1 up to mu n, it is a function of x1 minus x2, and we should also sum over this level over which descendant are we. Okay? And this I can write this by factoring out this C1 to 3 here, C1 to k, and putting a tilde here, and letting this be the ratio between the primary, the contribution of the primary, and the descendant. Okay, so again, all I did was I replaced these 2 points by a sum over primaries and their descendants, and this is what we get. So now, all I want to recall is that here only k equals 3 contributes. Right? In a CFT, we can choose the basis where 2-point functions are orthogonal. Therefore, this thing becomes a sum from n equals 0 up to infinity. Here outside C1 to 3, the same C1 to 3 as here. And then a sum over n, C tilde, mu1 up to mu n, 1, 2, 3. That depends on x1 minus x2. A bunch of derivatives with respect to x2, d mu1, d mu n, acting on the 2-point function, which is just 1 over x2 minus x3 to the power 2 delta. Okay? So on the one hand, conformal symmetry fixes this to be of this form. On the other hand, taking the OP of these two operators fixes it to be of this form. So the only thing I want you to take out of this is that by comparing both expressions, these C tildes here, the ratio between the contribution of a primary and of a descendant, you can determine it. You can fix it by symmetry. See, these two expressions must be the same. If you equate them, the C1 to 3 cancels out. But these C tildes, the contribution of the descendants, you can just find them out. For example, by expanding both expressions in x1, by expanding both in x1 or something. These C tildes are fixed by conformal symmetry. Okay? So what will they depend on? They will be functions, as we said, as of x1 minus x2. They will depend on the deltas. When you equate both, the deltas appear. When you are taking these derivatives, often you start getting Kronecker symbols because you take the d mu of x, and sometimes you contract Kronecker symbols so the dimension of space-time appears. So these C's depend on dimension of space-time, on the dimensions of the operators. But they are fixed by conformal symmetry. Okay? So that's the only thing I wanted to take out, is that the C tildes are fixed by conformal symmetry. And this has very important implications, because now consider a 4-point function, O1, O2, O3, O4. Okay? And consider again that you do the OP of these two guys, only these two, don't do immediately the last two. What will happen? Exactly the same thing, let's go here. What happens if instead of O3 we have O3, O2, O3, O4, nothing special, O3, just here you would have O3, O4. Is it clear? So what would we get? We will get a sum over k, C1, 2k, the same thing as there. Now let me take out CK, 3, 4, but then I will have, whatever I will put here, I will divide by CK, 3, 4, because this is not there. And then what do we have here? Here we have a sum over all descendants from n equals 0 to infinity. This C tilde, mu1 up to mu n, that depend on x1 minus x2. This is fixed by symmetry, remember? So this is totally fixed by symmetry. And then a bunch of derivatives, d mu1, d mu n, with respect to x2, acting on a correlation function, OK, O3, O4. And note that I divided by the structure constant, so this is again just a bunch of power loss, like here. So this object here, complicated as it might be complicated to sum it. This object here is totally fixed by symmetry. And this is what is called a conformal block. Okay? So a conformal block is a function that is fixed by symmetry. It's just one function you compute once and for all. It's a function that depends on what? So now let's be a bit more careful. So there is one difference here. Here we had the three operators being scalar, and this k was a scalar operator, otherwise this 3-point function here would not be 0. This has to be the same primary. But now here this k can be an operator with spin here. There's no problem in having a 3-point function with an operator with spin and two scalar operators. So this k here, we should think of this sum as a sum over operators of a given dimension and a given spin over primaries. And this conformal block is a function that depends on the dimension, on the spin, and then we can put some 1, 2, 3, 4, because to remind us that it was in the channel where we fused 1, 2, and 3, 4, so it knows about the dimensions of these operators. And it's a function of the positions xi, but this is a totally fixed function. It has several parameters. It's like an hypergeometric function. It is fixed. And indeed, it is an hypergeometric function, as I will show you when I will leave this lecture. So this conformal block is just a function, like Bessel function, hypergeometric. It's totally fixed by symmetry. And we see that a 4-point function can be written as a sum over delta and spin, and the fundamental building blocks that appear here are the structure constants and the dimensions of spins of exchanged operators. So these are really the two fundamental building blocks. The structure constant that tells you how operators interact, what's the 3-point function of three operators, and the dimensions and spins of operators, which is the spectrum of the theory. Okay? So this is the spectrum. These are the OPE structure constants, which are the same as the 3-point functions that we see. And together they form what is called the CFT data. And if you know this CFT data, as we see very explicitly, you can build correlation functions by using the OP, and by summing over all your primaries of the theorem. Okay? You probably saw all this in a Hugh Osborne lecture, isn't it? You saw all this already. Any question here? No? So let me, yes?
When you act by derivatives on a primary as on the left board, do you always get an operator with definite scaling dimension?
Yes.
No mixing?
If the derivatives are outside, so if you have an operator O that has some dimension delta, the operator d mu of O has dimension delta plus 1. So if you have an operator O such that the dimension of O is equal to some delta, the dimension of d mu 1, d mu n of O is just delta plus n. Okay? In other words, p mu, the momentum, commutes with delta to give back p mu. Okay, so very explicitly, for example, let's focus now in 4 dimensions, and in the case where all the external operators have the same dimensions, just for simplicity. So for simplicity, let's consider all delta I to be equal to delta. This does not mean that all operators are the same, but they all have the same external dimension. And let's consider 4 dimensions, which is interesting for us for n equals 4 super n mills, of course. Then, this correlation function of O1, O2, O3, O4 is given. Well, there is an explicit dependence, x1 minus x2 to the power 2 delta, x3 minus x4 to the power 2 delta. This is just some factor that with this factor, this guy already has the right scaling with respect to the conformal group. And then we have the interesting part, which is the reduced amplitude that depends on cross ratios, z and z bar, where these guys are cross ratios. So these are ratios of distances that are invariant on the conformal transformation, so we cannot fix this function. So we have cross ratios only starting at 4 points, so they appear for 4 points only. And then reduce the problem to a function of 2 variables, and then this A here is equal to a sum over all operators delta and L, structure constant 1, 2 into the operator delta and L, structure constant of operator delta and L into 3 and 4, times the conformal block, or a reduced conformal block after we take out this trivial space dependence that depends on delta and L and only on Z and Z bar. And again, this guy is totally fixed by symmetry, and just to be totally explicit, here it is. So this guy is just, you work this out that I explained you to do, and it is just a product of hypergeometric functions. Okay? So it's not so complicated. It almost factorizes Z and Z bar. Z and Z bar are defined here in terms of cross ratios, downstairs, you see. Z bar is a cross ratio, 1 minus Z bar is another cross ratio. And it almost factorizes if it was not for this factor here, which is Z minus Z bar downstairs. Here you have something of Z minus, and then you subtract the same thing with Z and Z bar exchanged. So it has a nice limit when Z goes to Z bar. And this H is just an hypergeometric function. Okay? So this is the claim. If you have a 4-point function, all you have to do is you take your 3-point functions that you compute no matter what, you take your spectrum and you sum it with these known hypergeometric functions. Okay? Very good. So just one more comment, that this CFT data that we have here is not totally unconstrained. You cannot just come and tell me, okay, I will define my CFT by giving you a list of deltas and cis, and you will just say, okay, the deltas are, I don't know, the ages of people on Earth, and the cis are whatever, something random as well. This will not work. And it will not work because it will not respect associativity of the OPE. It will not respect the fact that for the consistency of your CFT, you must have the freedom to OPE in different orders and get the same result. More explicitly, I chose to fuse operator 1 and O2 and then O3 and O4, but I could have chosen equally to fuse in the other direction. And this equality is an non-trivial equality, and these are called the bootstrap equations. So if you want a definition of a CFT, which is an non-Lagrangian definition of a CFT, is a set of numbers, deltas and cis, that obey the bootstrap equations. This is a definition of a CFT. If you have a set of numbers, an infinite table of numbers, deltas and cis, that obey the bootstrap equations, this defines a consistent set of correlation function of local operators in a theory. This can be your definition of a CFT. Yes?
The proof that that's sufficient?
Yeah, then it is sufficient. If you have 5 points, you can iterate it, and you can show that this is sufficient. Now, there are other conditions if you start requiring to do fancier things like putting your theories on funny manifolds. Then you can have funnier things. But if you are just interested in Euclidean correlation functions of local operators, then this is sufficient. And what is our goal? Or one of our goals? Our goal is to plot the CFT data of planar n equal 4 super Young-Mills at any coupling. And this is a tooth coupling that is conveniently normalized like that. So this is the goal. The goal that many people are trying to pursue in this moment at this time is to solve completely a 4-dimensional quantum field theory, and one of the things we would like to know is how to compute correlation functions exactly, and in particular how to determine exactly this CFT data. Okay? We want to know more things about the theory. We want to know Wilson loops, scattering amplitudes, many other things, but this is one goal. Okay? So let me remind you about some developments in this direction about concerning the spectrum problem. The problem of dimensions only. Okay? That's a simpler problem. So, but is there any questions so far? Is it clear? Am I going too slowly? This was all probably in Osborne's lectures, right? Am I going too slowly? Yes. I see some people don't know. I see. Right. Anyway, So for the spectrum, as I said, I'm going for the spectrum, we will consider in this lecture only two kinds of operators, basically. Some trivial operators, which are BPS operators, which are the kind of operators that Shine alluded to briefly at the end of his lecture, saying that some operators are protected by sypersymmetric. They were very important at the beginning of ADS-CFT to study the spectrum of ADS-CFT and so on. And another class of operators that are not protected, they are very interesting operators, they are totally non-BPS, they have an untriggered interpolation between weak and strong coupling, which are operators in the so-called SL2 sector. That Collier probably discussed at length the spectrum of this kind of operators, right? Through P mu and so on, how to compute the spectrum of operators that have some spin S. And these operators are basically trace of some number of derivatives, ds, of some number of scalars, z to the L, and then all possible arrangements of where to put these derivatives and these fields. So let's say plus permutation, where this d is some node covariant derivative. It's just a convenient way of packaging symmetric traceless tensors. So this d, which we conventionally, which is a null derivative, it is just n dot d, where this n is a null vector. We'll call it plus c. Okay? And then you might ask, what is the spectrum of these operators that are operators? So these are operators with spin S. What is their spectrum? What is their spectrum in, say, perturbation theory? Okay? So from now on, now I want to describe a little bit what the spectrum is, and I already have it prepared in the second blackboard, so let me just list it. I will try not to erase the blackboards in the back, because I see that some of you are taking notes, then at the end you can take the notes from the blackboards in the back. But remind me not to erase them if I'm about. So here is the solution to this problem. So how do we compute the spectrum, the dimensions of these operators in perturbation theory, say, to an arbitrary high loop order? So here is the answer. It looks very simple. So delta is just, so let's see, L plus S plus something that has G. So if you put G equals 0, it is just this, L plus S. That makes sense, right? So you just have the dimension, it's just a classical dimension, L plus S. Each derivative counts with 1, and each complex scalar Z counts with 1. And then plus some quantum part, which is a sum from J equal 1 up to S of some numbers, x plus J and x minus J, where x plus minus is some function of uj being what is called the beta rapidity. So now we have to absorb some notation, there's no way out. But we will explain the physics of this in a minute. This x of u, this x is a so-called Joukowsky variable that you also saw extensively, I'm sure. X of u is u plus square root of u squared minus 4g squared over 2g. Very good. But now this is of course not the solution. I did not tell you what these uj's are. If you put random uj's here, you get a continuous spectrum. Of course we have a discrete spectrum. So what fixes these uj's? These uj's must obey this set of equations. E to the I, P of uj, this is a function P of uj times L times the product of S. Let me call this P momentum and this SS matrix for reasons that will become clear in a minute. This product here must be equal to 1, and this is one equation for each j. So we have j variables and we have j equations, j from 1 to S. Okay? Plus an extra equation, this might look a little bit too much, but this is just a constraint on the solutions to this equation. So there are enough equations to fix these u's. And these are not new variables, they are defined in terms of, again, this beta rapidities, this x plus and x minus, and a function of x plus and x minus. And there are a couple of dot dot dots that I will not worry. I will not worry about what's called the dressing phase because it only starts at 4 loops. And I will not worry about these dot dot dots that are so-called wrapping corrections that Cole also described in detail. All because that just starts at very high loop order. And we are interested in starting to study these objects for now at weak coupling where what I wrote is enough. If the operator is large, this is enough at up to very high loop order. Okay? So mathematically, is this blackboard clear? This is the prescription. You have to solve these equations. Once you find the uj's by solving the second equation, you plug it into this expression for delta, and you get the spectrum of the theory. Okay? Now, what is the characteristics of these equations, even though this you probably heard like 10 times already in this school. So how should we think about these equations here, which are called Bethe equations? So let me put an hashtag, we will need this. So let's discuss a little bit the so-called Bethe equations. The way to think about it is to think of this operator OS as a bunch of scalars Z that you think of forming some kind of lattice, like some condensed matter lattice. So you have a bunch of Z's. And on this lattice Z, you put a bunch of derivatives, some derivatives. And then these derivatives move freely. You can put them at any position, and then you have a linear combination of many of them. These are these plus permutations here. Or you can think in momentum space. You can give each of them some momentum P1, and this guy some momentum P2, and this guy some momentum P3. And the dimension of this kind of operators is basically the energy created by this operator. You can think of it as this derivative kind of moves in this lattice, in this spin chain, scattering with the other derivatives, and the energy is the sum of the energies of these kind of spinance-like objects. And there are S of them. So this kind of sum that we get here is nothing but the sum that we are getting here, and Uj is just a convenient parameterization of the momentum Vj. So Uj and Pj are just the same thing. One is parameterization of the other. And what about, how do we fix the moment of excitations on a lattice? Well, we impose the fact that the lattice is periodic, because here we have a trace, right? So the trace is periodic, we can always rotate operators around. And because the operator is periodic, as you take this operator, as you take one of these derivatives and carry it around the spin chain, it scatters with the other derivatives that might be there. And the total phase should be equal to 1. And what is the total phase? It's a propagation part, e to the I p times L. This is this factor here. And then whenever it meets any of the other derivatives, it scatters with it, and you get a product of S matrices. A phase shift whenever it encounters any of the other particles. Okay? So this is kind of the physical picture, the way we should think. This operator has some inner degrees of freedom, so it has some self-energy, some inner energy because of these derivatives moving inside this spin chain. And these derivatives scatter with each other, and therefore the quantization condition for the multi-particle wave function gets modified from the free condition, that will be just this equal 1, to this more interacting part. And this momentum and S matrix are really the momentum of the excitations and the S matrix of the excitations. Okay? Is it clear? So can someone that does not know the answer guess what this condition is then? This product from J equal 1 up to S into the IP equal 1? Someone that did not think about this before. Someone try to guess? Sorry? Empty set? So can okay, so can someone that already thought deeply about this remind us what is it? So what would this be? This is a condition telling you that the total momentum is equal to 0, right? It's just you sum over all the momentum and it's equal to 0. So this is just because we have a trace. A trace is a condition that if you rotate everything by 1 unit, it's exactly the same thing. It's stronger than being periodic. Periodic, it's a ring. You go around and you come back to the same position. Here it's stronger. It's a statement that we only want states of the spin chain where we shift the spin chain by 1 unit and we get the same state. Okay? So these are only states that have 0 momentum. Okay? So this here, I want to emphasize, it's stronger than product from J equal 1 up to S, e to the I P of Uj times L, okay, equal to 1. So this would be the condition that you take your system as a whole, you translate it by L units, and you come back to the same. This is periodicity. This, there is no L here. Okay, it is just shift by 1 unit. So this first equation actually follows from this one. It is just a statement, if you multiply all bit equations, the S matrices cancel out between interacting particles, and you get just a movement of the system as a whole. Okay? It is just like you have a tennis ball full of particles. The tennis ball is periodic by itself. All the self-interactions cancel out when you consider the tennis ball. But this is a stronger condition that the momentum is equal to 1. Okay? So you should select out solutions of those equations where the momentum is equal to 1. Finally, so this is a comment about the physical meaning of these equations, and now I want to make 2 further comments. One comment about the fact that these equations admit several solutions. What does it mean from the field theory point of view? And another comment about how would we derive these equations. Where did these equations come from? Where did this expression for the momentum, the S matrix, and so on came from? So first about the fact that these equations have several solutions. So the only thing I want to say is that that is perfectly fine and welcome. Because of course we have different primaries. Just specifying the spin, there are many ways of redistributing these operators. So the fact that there are many solutions, so the different solutions, so the number of solutions to the Bethe and ansatz equations correspond to the different primaries of our conformal field theory for a given spin S. So for example, for L equal 4, where this L is what we call the twist, and for spin equal 2, 4, 6, 8, 10, so let me consider even spin, the number of solutions, just so that you get an idea. It's not, I don't know what its analytic expression is, but for example, for this, actually I have here all spins. 3, 5, 7, 9. From 2 up to 10, the number of solutions is 2, 2, 5, 4, 8, 8, 13, 12, and 13. Okay? So the number of solutions as you increase the spin, okay, it tends to grow, and it's some funny number, and you can check that this is exactly the number of primaries of your theory. Okay? So this is one comment. And the second comment is that these operators O, S, how do we find the operators with a fixed dimension? We diagonalize the spin chain Hamiltonian that corresponds to the dilatation operator of our field theory that we can compute in perturbation theory. We just do Feynman diagrams. We have an operator which is a single trace operator, which is like this spin chain. You see, remember each spin chain side is one of these Z's, eventually with derivatives on top. And we have another of these guys on the top. And we just compute 2-point function with doing Feynman diagrams. And if you are at one loop in leading order, all you care is about nearest neighbors, otherwise the diagrams will not be planar. And therefore you compute this Hamiltonian, okay? And you find that the Hamiltonian, that this that the problem of computing the spectrum is the same as the problem of diagonalizing this spin chain, which then is diagonalized by means of this Bethe and ansatz, where the map between these spin chain states and the operator O is pretty obvious. It is just when you have Z's it's vacuum, when you have derivative it's some excitation. So let me be a bit explicit. So you have an operator O at some point of space-time X, okay? And let's say this is a sum over the positions of where do we have derivatives, n1 smaller or equal to n2, smaller or equal to dot dot, smaller or equal to ns, up to L, put the derivatives in these positions. Some wave function that tells what's the probability for putting the derivatives in those positions. And then some operator that has derivatives at positions n1 up to ns, which is the same as the cats, where we specify that at positions n1 up to ns we have an excitation, with a small subtlety that will be relevant in 2 lectures, but I want to point out immediately, which is that you can have 2 excitations on the same side, or 3 excitations on the same side. A bit like Chance electrons, you could have an up and down electron at the same side. Here they are bosons, you can have many derivatives on the same Z, of course. And the conventions that we use is that this operator, say n1, n2, ns, is again a trace of z, many z's, and a derivative. Here there are n1 minus 1 positions, and then many z's, a derivative, and here there are n2 minus 1, etc. But if both derivatives are on the same side, you put a factor of 1/2, and if three derivatives are in one side, you put a factor of 1/3 factorial. So you just put here a factor 1/mj factorial, j equal 1 up to L, where mj is the number of derivatives at site L. It's just a definition of this operator. Okay? So mj is the number of derivatives at the jth scalar. And once you have this map to a spin chain, which is just, of course, a matter of language, what matters is that because of perturbation theory, your spin chain is local. Because of planarity, you cannot have a Feynman diagram where this leg talks to a very far away leg. You have to cross the diagram, it will not be planar. And therefore, this Hamiltonian H is a sum from I equal 1 up to L of an Hamiltonian density that acts on sites I plus 1. This is at one loop at order g squared. And then at two loops we start getting interactions a bit more non-local at order g to the 4, and so on. So what we get is a system of an Hamiltonian whose range grows bigger and bigger with perturbation theory, starting at one loop with an Hamiltonian that just interacts on two neighboring spins. So at most it can change a little bit where the derivatives are. It can hop them or not hop them. And then at higher loops it starts, the range starts growing. Okay? And the Hamiltonian, now you can compute. You do Feynman diagrams and you compute what this HI plus 1 is. Okay? And this is what you find, this HI plus 1. Okay, so this is this H, let me use this same. This Hamiltonian density acts on A derivatives and B derivatives, either by doing nothing, not hopping, and then the weight is just some harmonic numbers, or by taking some derivative from A and putting them on B, or taking from B and putting them on weight, with some weights, which is how many derivatives hop. Okay? And the claim is now that if you take this Hamiltonian, put a bunch of particles with some momentum and so on, this is an integrable system, and particles will scatter. The S matrix will be given by this expression. The spectrum will be given by this, by solving this equation. Okay? So now there's a lot to digest, and the simplest thing is either to prove or to check on a simple example such that we become convinced that this is correct. So now I'll go to Mathematica, and in the rest of today's lecture, I have 20 minutes now, right? I started 45 minutes. So, in the rest of the lecture, I would like to cover these two first subsections of the notebook. One of them called the Bethe ansatz and the one-loop spectrum. Let's study these equations and get familiar with them and see how the spectrum, how to compute the spectrum at one loop, at leading order in perturbation theory. Okay? Let's expand these equations to leading order and solve them. And then let's play a bit with this Hamiltonian and see that indeed diagonalizing this Hamiltonian gives the same thing as this more straightforward approach of just solving bit equations. Okay? So everything is done. So all I'm going to do is show you the code, give you a flavor of where this came from, and we can play a little bit with it. You can also play with it at the same time. Okay. So who has the notebook open? Okay, it's quite a few people, that's good. So let's see what we have here. So is the zoom big enough, or should we want it to zoom even a bit further? Is this better?
Does anyone need a mathematical file?
Here, done. Is this zoom better, or is it better 120, or this? Which one is better? This?
Yes.
Okay. So how do we solve these equations here? So well, let's first see that we want to do. Can you see if I point here, or it's too dark now? I might change it. Maybe it's better to turn on the light. But let me make a few comments before to be ready to address these equations. The first comment, let's go now to one loop and see that at one loop things become much simpler, of course. So at leading order, this x of u is just u over g. So x of u and u is the same thing, basically. You can just take that square root and replace that square root by u. And therefore, what happens is that this becomes just u plus I over 2 over u minus I over 2 to the L. And this factor here is suppressed in g, so this factor here you can drop. It is just 1. So you get just this rational function times this rational function equal to 1. And then here you can also put this u plus I over 2, u minus I over 2. Now, the way to solve this, now there are several ways to solve this equation. One of them is the following. You take the log of the equation. Okay? How do you solve this equation without S matrix? E to the I PL equal to 1. You say that P is 2 pi n over L. And the n is so-called the mode number. It labels the solution. Right? So it doesn't mean that P equal to 0. You can have P equal 2 pi n over L. And now you do a deformation of this. You just say that, okay, now I slowly turn on the S matrix and I still label them by the free mode numbers. Okay? So this is a convenient way. So now let's go here and I will just tell you a little bit what this is about. So what we are doing here, let's run this first cell, Shift Enter to run. To open the section, you double click here on the side. So now, if you don't know Mathematica, you should just try to follow and get an idea of what is going on. I'm not going to teach any Mathematica. So, but let me show you what these functions are doing. So what these functions are doing is the following. Here are Bethe and ansatz equations. Let's look at this one here. Can you see when I select like this, or it's better not select? Is it okay? So here we have an equation, 2 pi n. These are these mode numbers that I said. We take the jth mode number, so we take a table of equations, j equal 1 up to s. But then we have all these arctangents. Okay? And arctangents didn't appear here at all, but this is rather straightforward. It is just that log of x plus I over x minus I, or I over 2 if you want. So let's say, for example, this when you take the log, you have this u plus I over 2, u minus I over 2, and if you have 1 over I, and if you ask what is the plot of this guy, okay, this is this. And if you ask what is the plot of arctangent of x, okay, of 2x minus, then plus pi, x over 2 pi and x over 2, no, 2x equals. Okay, and then you see that it is the same as the other one for positive x, and for negative x it differs by 2 pi, right? So here I added pi, if I subtract pi I get one that agrees on the other side. So up to 2 pi, I am not lying if I replace this log by an arctangent. But the 2 pi I don't see if it is in the exponent, so I have the right to do it. Okay? So I just replace this equation by exponential and a bunch of arctangents, both here and for the S matrix. And then the way to think is that these equations are telling you that a sum and then these equations are telling you that L times some function of uj plus some interaction arctangent of uj minus uk equal to some integer n. So the way to think about it is that the first term the way to think about this equation is like some electrostatic equilibrium condition. You have some particles at some positions uj. L times arctangent of uj is some external force. Nj is the mode number, n is also some external constant electric field. And then the sum over j not equal to k is some interaction between these particles. This arctangent has the nice feature that arctangent at 0 is equal to 0, so it's a force that is not repulsive. So what we have here is a condition that we specify different external potentials and we get different electrostatic equilibrium conditions. So what is done here is we ask what are the mode numbers that I should choose for, say, length 4 and spin 4. And I get a list of mode numbers. And these are the mode numbers that I should use to label my 5 solutions for length 4 and spin 4. If you remember the number of solutions that I put here, for spin 4 and length 4, indeed there is a 5 there. It's 2, 2, 5. And these are the 5 mode numbers. Okay? They are not integers, they are half integers, because when you go from arctangent to log, sometimes there are pi's, so sometimes the numbers can be half integer, but that's a triviality.
Why they all different?
Yeah, they are all different because arctangent is 0 at 0. So if you want the rapidities to be different, you have to choose different mode numbers. Otherwise the rapidities will be on top of each other. So these are the 5, for each set of mode numbers now, you solve the corresponding equation. Okay? And what is being done here, you see, I have a subset of mode numbers, because when you write this equation, arctangent plus a bunch of arctangents equal to 0, arctangents go between minus pi and pi, so there is a range of solutions. So the mode numbers must be inside this range, otherwise for sure there will be no solution. It's like saying there is a brilliant zone. Okay? So I just have to choose mode numbers. And out of all these mode numbers, I select the ones, this mod L equals 0 is selecting out the 0 momentum states. Okay? So this is what these mode numbers do. Now if we ask what are the beta roots for 4, 4, I get a list of numbers. It becomes a bit too hard to see on string because we have precision 150, so we have 150 digits for each of them. And it might look a bit insane why we are doing this, but it will become clear in 2 lectures also. And here I put /n to make the precision a bit more reasonable, and you see that for each set of mode numbers, this is the first set of mode numbers, here is a set of beta roots. Okay? And once you have this set of beta roots, you compute the spectrum by doing this, by taking each beta root, square plus 1/4, this is just this term plus this term, when you put them together, when x is just u plus I over 2, it gives a Lorentzi. You apply it to each of the roots ul, and you sum them all. Okay? Some fancier way of doing this. So if I now ask, finally, what is the spectrum for spin 4 and length 4, let's put /n so that we can see, we have 5 numbers. So for each set of mode numbers, we got a set of beta roots and then 1 energy. So these are the energies for length 4 and spin 4. So there is some degeneracy, so there is 15 and 15 appears twice, and here is the energy spectrum at 1 loop for this spin chain. Okay? So now we can, I don't know, we can do all sorts of fun things like plot S, spectrum, say length 2, for example, if the length is 2, well, let's do length 4. Length 4, spin S. I don't care. We can do a lot of fun things. We can plot stuff if you want. Okay, very good. Any question here?
Sorry, 2-5 or?
Sorry?
2-5 or?
2-5? No, it's written here upstairs for even spin. I was working out yesterday in the plane what was the condition for odd spin, but I didn't finish, so it's even spin only. There is no odd spins in this theory. I'm joking there. Okay, but we will not do the mention. So this is the spectrum, so we can ask, say, 2, 8, for example. So this is the spectrum of operator of length 2 and 8 derivatives, for example. And it has only 1 operator. This is a famous fact. Twist 2 operators, there's only 1 primary. And indeed, we get 1 number only. We can ask 100 derivatives. This will take a little bit longer. This has to solve 100 coupled equations. And it is solving these 100 coupled equations, each of them with 150 digits of precision. So it will take probably a few seconds. And here it is. You get this 41.4. And the second time you run, it's immediate because it is saving the value here and so on. You can play with the notebook later. And then we can actually see that this is actually a rational number. Which is clear, you should have guessed, of course. But this is actually a rational number. And if you ask, for example, let's say the spectrum for twist 2 and spin S, let's make a table from S going from 2 to, I don't know, 40 in steps of 2. And this is boring, so let's put some dynamic S to know where we are. And I see 28, 30, 32. Now it's a bit funnier, not so painful to watch. And then we can see that they are all rational numbers. Okay? And of course, if you look at these rational numbers, no, but this case is so simple that you guess that immediately they are 8 times the harmonic number of spin. Just a check that, which is a known fact people knew already for some time, that the dimension of twist 2 operators primaries are 8 times the harmonic number of x. Okay, so this is just to see that the code is working. If you take any of these numbers, in general, they are not rational numbers. So if you ask rationalized for twist 4, they are not rational numbers. They are just some messy numbers, result of solving these algebraic equations, and they are just what they are. Yeah, plenty of time. Very good. Any question here? So is it clear how the code works? And of course I'm not explaining in detail all the factors, but it should be more or less clear. So the arctangents are just from logs of these rational functions. This ends is just selecting all solutions with zero momenta. Here we have some find roots, so we solve these bit equations with some random starting points, with some working precision. We do it as many times as there are sets of mode numbers, and the spectrum is the sum of all solutions. So it's a relatively short code to find the spectrum at all.
Why is it better to use arctangent than just log?
So what is the difference? So this is just a convenient way of thinking. So what is the difference in arctangent and log? Log was this function. Well, let's plot again. I shouldn't have erased, but this is something that I'm addicted to erasing stuff in mathematics. People that work with me know this very well. So this is the plot, and this is arctangent. So what is the difference if you take the log of both? In both cases, you take log and you get external potential plus some force equal to some mode number, which is again some force. But now you have to interpret these electrostatic equations. In one case, if you take arctangent, what is the force? The force is repulsive. The force is positive when x is positive and negative. It's attractive. Okay, that I'm not sure. It's probably... doesn't matter. So the force when the two particles are on top of each other, they don't repel. But then when they are separated, let's say the sign will multiply the equation such that they repel otherwise. Whereas here, it's different. Here particles don't want to be together because at zero there is some force. So as they are approaching each other, they are kicked to the right, and as they are approaching from each other, they are kicked to the left. So the difference between the two is just some shift of mode numbers. So if I use arctangent or not use arctangent, the way I would choose these mode numbers to solve the equation would be different. So for example, the fact, if you notice, my mode numbers were all different. This was what Collie was asking. Why are my mode numbers all different? And that's because I use arctangent. So the solutions of bit equations, these solutions they use must be all distinct from each other. Otherwise, this is not a physical solution. The state doesn't exist. The wave function would be zero. And that you can enforce in the arctangent picture with different electric fields. And in this picture, you can put the same electric field. There is a potential. And it's like these traps of cold atoms. But the atoms, because they repel each other, they become different even without choosing different mode numbers. So it is just the function to choose the mode numbers would be a bit different. And it's much easier to solve numerically when your function is smooth like arctangent than with log. So these are two reasons why I think arctangent is much better. But it's the same. If you also know a reasonable starting point, you can also solve the equation in the product form. But then you have to make sure that you capture all the equations. I mean, there are many ways of solving these equations, of course. This is just one fast way of doing it. More questions? So now in the remaining 10 minutes, let's see, what about the Hamiltonian? So the Hamiltonian is much faster, you see. So the Hamiltonian, the Hamiltonian, we define it here. Okay. So this Hamiltonian, it acts on a state, doing what? It takes the state, it looks for, okay, I should first start here. So we are going to use the following notation, 0, 0, 0, 2, 1, 0, 0. This will be notation for z, 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 two derivatives on z, derivative on z, and then 2z's. Okay? So this is the notation we are going to use. Is it okay? Okay, so we are going to use this S to denote the cats. And this is, of course, equivalent to, in our mind, this is the same as the cat 0, 0, 0, 2, 1, 0. Okay?
Sorry, probably second time it shouldn't be square.
Yeah, second time this. Thank you. Very good. Okay. So this is the notation we are going to use. And what does this Hamiltonian do? It looks for anything that is S of something, that is a cat, and does the following to that something. It sums from 1 to L, this is Hamiltonian density sum, and then there is a sum from D equal minus to plus something. This is the maximum hopping from right to left or from left to right. If there is no hopping at all, a sum of two harmonic numbers, H is a harmonic number. Otherwise, minus 1 over absolute value of how much it hops, and then you replace in the cat position I by whatever was there minus whatever hopped, and position I plus 1, whatever was there plus whatever hopped. Okay? So this is just implementing this Hamiltonian here. Let's see how it works. So S 0, 0, 0, 2, 1, 0, 0. Let this be the state, or say 2 times this plus 3. Plus 3 times the same times, say, I don't know, here. This. And now let's apply the Hamiltonian. Okay? This state has length 7, and we apply the Hamiltonian to this state. Okay? And this is what we get. We get a bunch of terms. We can expand if we want, or not expand. Then we can have an idea that we get an Hamiltonian, the derivatives hop. Maybe let's act on a simpler example, just this, for example. And you can see that the derivatives hop. We have one term. The first term with 3 means that the two derivatives hop on top of the 1. Or the 1 hopped on, it's rather the 1 that hopped to the position. No, it's the 2 that hopped there. 2 derivatives hopped there, so it's 1/2. The other one, 1, 2, is the one that hopped to, it's one derivative that hopped and so on. And you can easily figure out that all the terms are correct as they should be. Okay? Is it clear? So this is just implementing the Hamiltonian. Thank you. And what is this cat? This cat it is just a convenient way found. Say I have one derivative at position 1, one at position 3, in a spin chain of length 10, it creates the cat. Okay? It is just some convenient way because I prefer to use this N1, N2 rather than to have this huge string. So if I have one at position 10, another one at position 10, one at position 20, in a spin chain of 50, I get this. And you see there is a 2 here because I have 2 guys at position 10. Okay? Is it clear? 1 minute? And that's it. Okay. So now let's do a check. Let's do a check of this Hamiltonian. Okay? This is a fun check. And I erased too much, right? As usual. Okay. I told you I'm addicted to erasing. So the check is this, and I would like to go through the last 3 in some detail since I have 1 full minute. Okay. So this basis of 4, 4, for example, gives me a base of all possible states of total number of derivatives 4. 4 on the first side, 4 on the last side, or 1 on the second side, third side, and 2 on the last side, and so on. This gives me a base with a given length and a given number of electrons, bosons, a given number of derivatives. And now let's suppose we want this Hamiltonian as a matrix. Like we write a matrix acting on a base of states. So let's just build this ourselves on a particular example. So let's see what this stuff does here. So what this does here is the following. So suppose we take our bases of length, say, 4 and 6. Okay? And we apply the Hamiltonian. We apply the Hamiltonian of length 4 to each element of the bases. Then to each element of the base, we get some complicated thing. We can see this in table form. This is a list to each element of the base. The Hamiltonian acted and gave me something. And now what do I want? I want the coefficient of this in some element of the base. What's the coefficient in a given element of the base? I choose the element and I apply this again to all the elements of the base. Okay? So this just gives me a matrix, okay? So I can ask matrix form, okay? So this is just a big matrix, this is the Hamiltonian. This is the Hamiltonian, all states of length 4 and 6 spins. This is what we have to diagonalize, okay? So if you want to see it, the Bethe, for example, can have a matrix plot, give some nice plot of this Hamiltonian, okay? So these are the elements that are non-zero, and we want to diagonalize this matrix, which has size 90 by 90 or something like this. Okay? So here we have, this is what we did. We compute the matrix. So this is this matrix, this is the same as this matrix 4, 6. Okay? The matrix 4, 6, if we ask to see how it looks like, this is what it looks like. Okay? We can also ask the matrix 6, 4, length 6, 4 spins. It's a bigger matrix, it's 120 by 120 or something like this, and this is how it looks like. So we have this way of generating these big matrices that we want to diagonalize. And now let's compare this with the spectrum. So let's compare. So this is the spectrum here. Let me run it and hide it again. So this is the spectrum of length 4, spin 6. Okay, all the states of length 4 and spin 6. Numerics, the union, and sort. And what we want is to compare with the diagonalization of this Hamiltonian. Okay? So let me work out this in detail starting from scratch. So we start with matrix 4, 6. And we compute the eigenvalues of this matrix. Okay? Now, the eigenvalues of this matrix is a mess, it's roots, blah, blah, blah. Okay, we can ask for numerical values, then it's a bit easier to read. And, okay, we can make union if we want. And we get some eigenvalues, and it is much more than the ones here. Okay? Here we get way more than the ones here. Okay? Why? Well, several reasons. One reason, for example, is that here we are diagonalizing this periodic spin chain, but we are not taking only the eigenvectors with zero momentum. We are taking the periodic ones, but not the ones that have zero momentum. So let's select out of this the ones with zero momentum. So how do? We take eigenvectors. Eigenvectors gives me what are the eigenvectors corresponding to these eigenvalues. Let's say we put some n here to make it a bit faster. So these are the eigenvectors, so we can take the first of them, this is what it is. Okay. And if we want, we can dot it with bases 4, 6 to see how it looks like in terms of our cats. So this is the eigenvector corresponding to the first eigenvalue, it's 28.7962. Okay? And now we want to check, does it have zero momentum? So what do? We take this eigenvector, and the same one where each cat, we rotate it by 1 unit. We rotate it. And we subtract both quantities. And let's see what we get. And we get is 10 to the minus 17, 10 to the minus 16, which is just numerical error. So we can ask just to chop. And we get 0. So the first one, for example, has zero momentum. Okay? It's good. Okay? So then what are we going to do? We are going to take the eigenvectors of this matrix. Okay? So these are the eigenvectors. And here are the eigenvectors as cats. Okay? So these are all the eigenvectors as cats. Okay? So if we take the first element here, gives me what we just saw, this eigenvector as cats. And then we check, we took for each of them, what we do here, for each of them, we check, we have this bool. Bool is a function that is 1 if whatever is here is true and 0 otherwise. If that something minus that something rotated is equal to 0. And now we get a list of 1s and 0s. The 1s correspond to the positions where we have a good state with zero momentum. The 0s correspond to the bad, where it does not have zero momentum. Okay? And this is what is done in the first line here. And then what we have to do is take the eigenvalues and multiply by that something. Okay? And now we can make n if we want. And now we get a list of smaller list of eigenvalues. The 0s you should ignore, so we can make, if you want, union. And now we have a smaller list of eigenvalues, and some numbers agree, you see. There is this 28, and there is a 28 here. There is a 24, and there is a 24 here. So it's almost perfect. However, we still have many more states here. Why? They have zero momentum, they diagonalize. Why do we have them? What could be why should we drop some of them?
Descendants?
Descendants. They don't need to be a primary. They could be something that was already contained with, say, spin 5, and we just acted with one derivative. Right? So if it is descendant of spin 3, it's also in the descendants of spin 5. So all we have to do is don't take this, but take the complement of the same thing that you would get if you take the eigenvalues of the case with 5. And when you do it, then you get exactly the same list. Okay? This removes the descendants. So you take the complement, you compute the eigenvalues and so on, and you get exactly the same as the spectrum. And I have to erase, otherwise I get crazy. Okay. So this is it. So this is what I wanted to tell you in this first lecture. So what we have seen is that we have a gauge theory, which is a CFT. We want to compute its CFT data, and the zeroth order point is to understand its spectrum and its anomalous dimensions. Local single trace operators in a planar limit can be mapped to spin chains, and it's convenient to think of them as spin chains. We can diagonalize spin chain Hamiltonians to compute its spectrum, but it is much better and much faster to use Bethe equations. To diagonalize, say, a spin chain of with hundreds of spins and so on, like I did, that took 40 seconds, would take age of the universe if I would use the Hamiltonian. So it would be basically unthinkable. And as we see, both agree perfectly. So now, if you want, you can try to check this equation, derive them carefully, or it is absolutely obvious that it works and you don't care. And of course, the best is a bit of both. Okay, so in the afternoon we will go on and start studying what do we need about these spin chains. We have this spin chain, we have a spin chain model of spins that halt and so on. This was all fine for the spectrum. We want energy levels of the spin chain. What about structure constants? What do we want to know about these spin chains if we want to know about structure constants? It's no longer just the energy levels. What is it? And this is what we'll start seeing in the afternoon. Thank you.